All right, good afternoon, everyone. Hope you enjoy Ray's Summit so far. So today, we're going to talk about AIBrix and DeerFlow and how these two work together. So my name is Li Guang. I'm working for ByteDance's compute infra team. We support my teams responsible for DPU, data processing unit, and the inference infra, and support all kinds of compute infra requirements for ByteDance's global compute business across the globe. So yeah, so as many of you know, the large language model, LLMs, contribute to drive the innovation and the next generation AI and agentic workloads. Infrastructure team, including myself, are facing growing challenge to drive performance, scalabilities, and also cost efficiency at production scales. And in this talk, we're going to cover AIBrix, an open source cloud-native solution purpose-built to deploy and manage and scale large language model inference with code design, with inference engine like vLLM and SGLang, and show AIBrix supports agentic workloads. So first, I'm going to give you a quick overview. So as mentioned, AIBrix is a cloud-native solution optimized to deploying, managing, and scaling model inference. Support inference engine like vLLM and SGLang. And DeerFlow, on the other hand, is an open source project, also open source by ByteDance. It's a multi-agent research framework designed specific for beginners, and it built on top of the popular LangChain ecosystem, combining automated and human-in-the-loop task plannings. And DeerFlow also integrate tools like web search, content readings, and Python execution, and support function expansion through MCP service. And these two projects, as mentioned, both are open source by ByteDance and has gained thousands of GitHub stars in matter of just months. So first of all, let's show you a quick demo how these two work together. And we're going to utilize a straightforward Q&A workflows that involve interaction between DeerFlow and AIBrix. And DeerFlow here will be the front end, and AIBrix is going to provide back-end endpoints for inference services. So let's check out this demo, right? And here going to be you're going to see the UI from DeerFlow, and we're going to pop up a very popular question: how many times taller is the Eiffel Tower than the tallest building in the world? And the planner here going to start generating a research plan and then sending to the large language model backend and generating a report about the height comparisons between Eiffel Tower and the tallest building in the world. And it's quite user-friendly. You can check out the DeerFlow's online websites. All right, and here we're going to show you some open source status for AIBrix so far. The image on the left is the original blog post we published on vLLM back in February this year, announcing AIBrix. And in the first week, it was trending pretty well, ranked #1 in the GitHub trending leaderboard. And also, it received quite strong support from the communities, right? We are very appreciate that. We gathered over 4,000 stars, more than 300 folks, and also nearly 100 open source contributors, and more than 50% then are actually non-ByteDance. We actually quite appreciate the external contributors. And it quickly evolved into a community-driven project. And for example, right, ByteDance team already initiated collaboration with Google and Red Hat within the Kubernetes communities, and to jointly advance the AI inference workload in the Kubernetes ecosystem. We also work with AWS team and to integrate AIBrix into AWS EKS, one of the largest Kubernetes service in the world. And together we demonstrated back in April in Netherlands in the SPRO Europe's 2025 conference, how to deploy DeepSeek R1 using AIBrix and run the model inference on AWS Trainium and inferential AI chips. All right, here is a layer view of architecture and for AIBricks. AIBricks introduced several innovations and to enhance the performance and cost efficient. First of all, on the top would be an OpenAI compatible API that serve as a unified extensible entry point to all the inference requests. And the second layer going to be AI gateway. That extend Envoy gateway will run on top of Envoy gateway extended to optimize instant routing and support various of routing strategy. And unlike the traditional gateway that distributed requests blindly, AIBricks analyzed the token patterns, prefill cache availability, and then compute the overhead to enhance the routing efficiency in diverse deployment scenario. And this scenario includes the fairness and load control, dynamic batching, and cache-aware of routing. Later on, I'm going to keep a little bit more deep dive into the routing part. And the third layer will be a model service layer, and that feature high-density LoRa management, which enable dynamic LoRa restoration and linkage support in vLLM, streaming the LoRa adapter management, and also reduce the cost of manage so many fine-tuning models. And the second to the bottom layer would be resource orchestration layer. We support various of scenario-driven autoscaling policies, and we also feature optimizations such as sliding window metric aggregations to reduce the propagation delay of the real-time metrics. And the bottom layer would be a distributed and disaggregated KVCache layer that introduce a distributed KVCache and enable high capabilities cross KV reuse while optimize the network and memory consumption. And we also come with a bunch of very useful tools. I'm not going to talk about that in detail, but please check out our websites, and we have a very detailed documentations to introduce every and each of them. All right, and previously I already showed a conceptual diagrams demonstrating the feature of AIBricks, but the actual architecture, the system architecture of AIBricks is much more complicated, composed of many cloud-native components that make it production ready. While I'm not going to talk about that in detail, you can also find information of these components in our from our websites. And since it was launched back in February, I think received a couple of key endorsements from the community, including Robert and also Clayton Coleman from Google. And all right, here is a very high-level overview of all the features we have released so far. So back, we have successfully rolled out 4 feature release and plan to roll another ones this week, the fifth release. And in the very first release, we focus on building the cloud-native foundation for AIBricks, tackling cold start latency with GPU streaming loaders, auto-scalings, and cost reduction with high-density LoRa. And in the second release, back in February 2025, that will be our very first step into distributed and disaggregated architecture, adding support for distributed KVCache and multi-node orchestration for DeepSeek R1s and heterogeneous servings. And in the third release, this May, we introduced our state-of-art KVCache offloading solutions, which significantly improve time to first tokens, latencies, and add advanced routing policy, like prefix caching awareness and fairness, along with our benchmark tools. And back in August, we have another major release focused on prefill decode disaggregations and KVCache V1's connectors, KV event, and multi-tenant support. I'm going to talk more in this talk about our latest, the 0.4 release. And this week, we're going to release 0.5, right? We're going to release the batch API, multi-model support, a storm service, and efficient KV offloading for both vLLM and SG lens. Storm service will be our production ready prefill decode disaggregation solution, which running in ByteDance production, support over 10,000 GPUs in production. All right, and overall, right, the goal would be very clear. We focus on two main objectives, which is lower cost for inference and as well as push the tokens throughput, the overall system throughput. Next, I'm going to talk about KVCache and PD disaggregations, and why KVCache matter here, especially for large language model inference, right? Because in real world large language model applications, the KVCache is highly reusable and extremely valuable, in my opinions. To put it simply, since LLM are built on transformer architecture, and each inference step leave behind some intermediate computation result. And if a feature request, right, share the same prefix with the previous one, then this result, the KV cache, can be reused to speed up the computation. That's as simple as that. For example, if in a chatbot or multi-run conversation, we often see repeated prefix sequence across requests. But the challenge here is, if the KV cache going to consume a huge volume of GPU memory, right? And the usage grow rapidly with model size and the context length. Take a 70 billion parameter model as example. If you want to support a 100K context window, the KV cache alone going to occupy hundreds of gigabytes of a GPU memories. And once this GPU memory, the limit is hit, then the inference engine going to start evicting some of these KV cache tensors and from the cache. But when those tokens appear again, we have to recompute them from the scratch, wasting a lot of GPU computations and significant hurting the performance. So to address these issues, AIBrix introduced two tiers KV cache offloading solutions. This is a two-tier KV cache hierarchy. We want to reduce the GPU's memory pressures and improve the reuse. And the solution right now is built on top of the vLLM connector APIs. And we have two layers. The L1, we have L1 cache and L2 cache. L1 cache is backed by a local DRAM and enable fast access within a single node. And L2 cache is extensible. It's an external service cache. We integrate with both ByteDance in-house KV cache solution like HPKV and PrisDB, and open source solution like Infinity Store. And all of them has been integrated. And we're going to release some of our in-house KV cache solution next week. And also with RDMA back storage, we can offload and retrieve a chunk of the size about 300 to 500 tokens around 1 millisecond, which is very critical for low latency workloads. We also support customer routing and evasion policy to ensure the hot chunks always stay close to the GPUs. And to make it very simple, right? The KV cache solution, now we offer three folds. One, we first support a pluggable evasion policy. And with it, you can design and experiment with different evasion strategies, from the classic LRUs to attention score aware of evasions, to achieve both efficiency and selective KV cache offloadings. And second, we also introduce a pluggable serialization engine, which allow you to study how KV cache compression and quantization algorithm affect performance. Third, we provide a pluggable connector, allow you to connect to different GPU backends. So I mentioned that we already support 3 backends within ByteDance, but you can also experiment different backends, right? Different SSD backend, network backends, as well as managed KV cache service. All right, now let's switch gear to prefill decode disaggregations. This technology has become like an emergence industry standard, right, for optimizing large language model serving. So I don't think we need to give too much introduction about this technique, right? In traditional setup, right, the prefill and decode stage share the same GPUs, causing interferences, especially when the large prompt going to slow down a small decoding task. And the prefill disaggregation was proposed to solve this problem by using dedicated prefill and decode workers, and each of them for optimized its own workload patterns. And this decoupling is very useful, ensuring the decoding latency stays stable even under bursted and prompt-heavy traffic. So in our test in AIBrix, enable the PD disaggregation can reduce P95 TPOT latency by up to 80%, especially in model, the large model like DeepSeek R1s, where the reasoning is enabled, output is long, and the decoding is going to dominate the task. And in our view, there's two main architecture for implementing PD disaggregation in AIBrix. One is the centralized one, the centralized KV store architecture, and the other will be the P2P architecture. Both of them are supported in AIBrix. So for the centralized one, right, after the prefill feeds, the result going to stop in a shared KVCache server, and the decoupled workers are going to pull the data from the store. And this architecture is used by Mooncake, as it scales pretty well across multiple nodes. And the PLP architecture, though, decode worker going to directly pull the KV result from the original prefill node. And this design avoid one more hop latency, but also introduce more tighter couplings and also limit the scalability. So there's no good and bad, right? So user can choose the right architectures that balance the performance and flexibility. Basically, it's a trade-off here. So, but both architecture has been supported by AIBrix. All right. So, as mentioned, PD disaggregation become the norm, and each serving unit is no longer a single port. It's a small distributed system with separate prefill and decode roles. And to simplify the design, AIBrix introduced the role group abstractions on top of Kubernetes, allow the developer to orchestrate prefill, decode, and optional local scheduler as one logical unit. This is going to help manage the complexity inside each inference instance. We also introduce some advanced feature to further in our orchestration layer. For example, we can support rolling upgrade across role groups, and also the network affinity and gun scheduling to keep co-located components performance. So technically, we support different replication, including SPYDs and pool mode, and also different inference engine, including vLLM and SGLens, and also support PD mode, as mentioned, the centralized one and the peer-to-peers, right? So technically, there's no blocker for you if you like to use Nixos or Mooncake in this case. All right, let's switch gear again to talk about autoscaling and routing. So autoscaling is quite common in the prefix-aware routing is quite common in the large language model inference. So basically, if you want to in this case, right, simple case, two nodes deployment case, if you want to hit the KVCache, a request must route to the instance that already hold the relevant KVCache. That means the router in any inference system need to know which port, right? Which port currently own the KVCache for a given prefix, so that it can dispatch the request correctly. Here is example. The first request is I like apples, and at this point, all nodes are empties and without any KVCache, right? So the request can freely go to any nodes. Let's say node 1, and node 1 now compute and store the KVCache for the sequence. And when the second request comes, and is a I like apple request, since the node 1 already has the cache KV, the router will have no blend, just forward the request to the first node, which already have the result. So the hit ratio, the cache hit ratio, going to be 100%, meaning there's almost no computations, and latency drop will be significant. Now we come with the third request. I like apple very much, and the first part is identical to the previous two, and in this case, you got two chances. One is you continue forwarding the request to the first node, and which going to bring you 50% prefix match, and meaning that you're going to use the KVCache partially. Second option is going to route to second nodes, which has 0 match, but that means you need to do a full recomputations. But now, even no one can reuse part of the KVCache. It's already heavy loaded, right? Let's assume it's already have the load is 50%, and the second nodes though has underutilized, only have 30% load, right? So how do you make the right routing solution decision in this point? Is a bit more complicated, right? So you need to export the trade-off between KVCache hit ratio as well as the nodes load. So to export this trade-off, we build a prefix-aware routing algorithm in AIBricks called Prefill. It dynamically decides under KVCache sharing environment which port each request should be routed to, and to balance the cache hit ratio, latency, and load distribution in real time. All right, and here is a quick architecture for the AIBricks routers. After every request route to the Envoy gateway, we're going to forward to the AIBricks router, and we're going to compute. We have a bunch of routing rules. We're going to compute that, and then find the target port IPs and send it to the Envoy gateway. And Envoy gateway is going to pick up this port and forward the request to. And to make it extensible, we support all kinds of make the policy definitions quite flexible and extensible, so that user or developer, if you want to try out your own routing policy, you can work on AIBricks and define your own policy. And the new routing algorithm will not require changing anything else but the code just on the policy logic. All right, we talked about the prefix cache. Now let's talk about some advanced stuff. It's a new feature introduced by AIBricks 0.4 release. It's a KV-aware routing policy. And the main goal remains the same, right? Is that the gateway can route the incoming traffic directly to the instance that already hold the relevant KVCache, and to reduce the TTFT and boost the overall system performance. The goal remains the same. But in the old design, the gateway itself need to maintain an internal index and tokenizer, and you're going to pass every incoming prompt or request and search for prefix match, and then route the request to the instance that has the corresponding KVCache. And this approach is a router-driven approach, fully decoupled from any inference engine. Like you can use SGLang, vLLM, it's okay. But it comes with a cost. And in an old design, in a new design, we're going to switch to an engine-driven routing mode. What does that mean? It means that the gateway no longer maintains the KV metadata on its own. Instead, you're going to synchronize the KV events directly from an inference engine, for example, vLLM, in real time at the milliseconds granularities. And we also leverage the KV event dispatch interface provided by vLLM to make this possible. And the advantage, why bother to doing so? The advantage is very clear that the KV information inside the gateway is now more accurate and up to date, right? And however, it also increases system complexity because it requires gateway to use the same tokenizer and as the engines. So ultimately, it's a trade-off again. It's not, there's no back and wrong about this. So if your workloads demands real-time KV synchronization, right, go with the new approach. But if you value loose decouplings from the engine, for example, you plan to support other inference backend in the future or want a fewer external dependency, then leverage the old one, and which may still a benefit for your scenario. So we support both the new one and the old approach. All right, now let's give a quick demo about how to put everything together. We talked about KVCache, offloading, we talked about prefill, decode, disaggregation, prefill, aware of, or KVCache, aware of routing, right? Let's put up everything together in a single demo. And we're going to demonstrate a workload where AIBrix is going to involve interacting with DeerFlow. DeerFlow, again, is a deep research framework. We already have a short demo at the beginnings. And this interaction is going to initiate a multi-round conversation between the two systems. All right, in this demo, we're going to conduct a research report regarding how many years, right, an average Tesla battery lasts compared with the gasoline engine. Let's see how DeerFlow conducts the research, generates a research plan, and after confirmed by humans, right, you're going to send the plan to the inference engine and going to generate a full report. And DeerFlow is very flexible. I encourage you to try out if you're doing some related research. It's designed to handle very complicated tasks in a very collaborative way. So through a set of special agents. And each agent responds for a specific function, like a planning, research, or coding, right? So it's in a matter of a few minutes, you can set up a DeerFlow front end in your local desktop, and you can choose a different back end, right? For example, AIBrix as a back end, or you can put it to Volcano engine, our own the ByteDance's cloud inference service, as well as OpenAI or others inference endpoint you like. All right, we're almost done for the research. Let's give it like probably 5 more seconds. I believe a report going to be generated. All right, then you get a report about an average Tesla battery lasts. How many years average Tesla battery lasts compared with the gasoline engine. All right, so before the scene, I'm going to give you a screenshot showing how AIBrix performs at the back end, right? So in this case, we're going to conduct an auto-scaling test. We're going to send a burst of a request to AIBrix, and which triggers pod auto-scaling, right? AIBrix can auto-scale and based on the load matrix, and in this case, going to start a new pod within 1 minute to encounter the certain and increase traffic and maintain the stability. On the left-hand side, you can see there's we basically print up the pod activities during that 1 minute. And during that 1 minute, basically roughly 5 to 10 seconds is the CUDA or C+ extensions. And for the model loading from the remote remote GPUs, going to take about 15 seconds. And the GPU, the CUDA graph capture and installation time is going to be 20 to 25 seconds. And the server going to get ready. After that, the server going to get ready about 5 seconds. On the right-hand side, you can see there's a bunch of metrics, requests per second, TTFT, TPOTs, P50, P95s, and also as well as the cache hit ratios within the AIBricks systems. You can monitor that and observe how AIBricks make those auto-scaling decisions. All right. With that, I'm going to conclude my talk. AIBricks and both AIBricks and DeerFlow both are open source, and we're very much looking forward to an open and friendly community and continue to driving innovation in large-scale inference infras. Thank you very much, and yeah, I'm ready to take any question if there's any if time allows. Yeah.
All right, thank you, Li Guan. We're at time now, but I'm gonna invite you to ask the speaker. Maybe outside or right here, offline. Thank you.
All right, thank you all.